Okay, all right, let's get started. We are in lecture 2. We are rocking and rolling. Let me get those adjusted. So I posted the attendance grades to Blackboard. So far it seems to be working pretty well. I mentioned on Monday that I'll either use the native feature in Blackboard or I'll upload them manually. And so the native feature seemed to work pretty well, so I'm going to go ahead and just keep on doing that. I went ahead and posted the lecture recording to the YouTube playlist. Let's also talk about our first homework assignment. I'm actually going to pull up the assignment today. It is really short. it's really short. It's literally one problem, and when I know sometimes engineering professors get a bad rap for there's only one problem. Problem 1, part A, part B, part C. It really is one problem. You'll see what I mean. But today what we're going to do is we're going to sort of continue the discussion that we had last time, but I want to more formally talk about load and resistance factor design. I want to talk about exactly what it entails, how to use it, and because we're going to be using LRFD for the entirety of the semester, and so just making sure that you are comfortable with it is something that I'm wanting to make sure is well communicated and all that. Okay, so with that, I took my keyboard off, so I'm a little hampered. Okay, so we're gonna go back to the notes that we sort of brought up last time, and I'm gonna go through the first part of this somewhat quickly because we went through it last time, but I do want to review it just to make sure that everybody's on the same page. On Monday, we talked about the idea of a limit state. And a limit state is a condition that we as engineers define such that if you have an element or a member, a connection, and you exceed that condition, then the member no longer fulfills its function. For example, we talked about columns, and we said a limit state might be buckling. So we can calculate the amount of load that it would take to buckle a column, and if the load that we put on that column exceeds that, well then, we say that the element has failed. So basically a limit state is just sort of a condition where we say either the member is good or the member has failed. And that those limit states tend to be defined based on 2 categories. One of those is safety. So in other words, or strength. So if you ever hear me use the term strength limit state, bless you. If you ever hear me use the term strength limit state, that means that if we violate that, we are putting the safety, health, or the welfare of the public at risk. So buckling of a column would be a good one. Fracture of a tension member, that's another one. Anything where if that member fails, people might die. That is a strength limit state or a service limit state, and it is for those types of limit states that we apply factors of safety and things like that. The others are service limit states. You might hear me use the term serviceability. Tends to mean the same thing. Those are things like ensuring the day-to-day intended performance of the structure. So are the beams deflecting too much to crack the plaster? For example, here's another one. While we're not going to get into this today, one of the things that we do have to look at, and it's kind of complicated. It's more of a building level thing than it is an element level thing. But if you're in a building that might be susceptible to, say, vibrations, we have limits in check to ensure that the floors don't vibrate too much. Because if you're on a floor and it's moving up and down, that's not very comfortable for you as a user, right? So if you are in a situation where vibrations are something to consider, you might need to change the design of your structure, not for strength, but more for human comfort, human perception, and things like that, okay? Now, this isn't a totally exhaustive list. There are some other limit states that come into account, particularly with steel. One of the other limit states that we tend to deal with in the land of bridges is a limit state called fatigue, okay? Now, every single person in this room, I believe, has experienced a fatigue-related phenomenon at some point or another. How many of you have ever drank Soda, Monster, anything in an aluminum can? I would say everybody. What is the easiest way to get the tab off the can? How do you do that? If you want to take that tab off, what's the easiest way? Do this, right? Take the tab and back, forth, back, forth, back, forth. And then what happens after a while? It kind of gets like soft, it kind of gets weak, and it just sort of pops right off. Y'all know what I'm talking about? Well, what's happening in the can is that when you take that element and you cycle it back and forth, you are introducing micro cracks into the metal right there. And so what's happening is as you're doing that, you're taking the metal and you're cracking it, so you're separating that ever so slowly. And it is a function of the cycles that you apply. And the more cycles you apply, suddenly it gets weaker and weaker and weaker, and at the very end, it just sort of falls off, okay? Now, that is an example of low cycle fatigue. You put it through a very small number of cycles, and then it fractures. Well, bridges are subjected to high cycle fatigue. I mean, think about it like this. If you have a bridge that's carrying traffic on, let's say, 3rd Avenue, how many vehicles go across 3rd Avenue in a given day? Take that and multiply it by 365 days a year. AASHTO says that we design bridges for a 75-year design life. Do the math. That's a lot of cycles, right? So you can have certain connections or stiffener plates or things like that that can fail at stresses far lower than what you would expect under just a strength condition because of those cycles. So if you ever have a situation where a structure is subjected to a lot of cyclic loading, you might need to consider fatigue. I just mentioned that just because I want to give you all a big picture idea of what's going on. All right. Okay. Last time we used the example of breaking some tables in the class, and we said, okay, let's say I'm designing a table, right? And I want to know what its capacity is. So a simple way of determining the table's capacity is I could take it down to the lab, you know, again, sort of like the hydraulic press channel on YouTube, put it under an actuator and just break the thing in half and figure out what force was required to break it in half. And so I mentioned a number, I said 800 pounds. Let's say it takes 800 pounds to snap this table in half, okay? Well, what I could do is say if 800 pounds is the actual capacity, I might say 400 pounds is its allowable capacity. And I would do that if I chose a factor of safety of 2, right? So its actual capacity is 800, its allowable capacity is 400. And the ratio is the factor of safety. And what that factor of safety is doing in that case is decreasing the strength. We could, on the other end, amplify the loads. Like if we were in a design scenario and I have a beam and it needs to support 3,000 pounds, I might design it to support 6,000 pounds. Again, whether the factor of safety is amplifying the loads or it's decreasing the strengths, it's doing the same thing. Okay? Now, that is a design philosophy. A design philosophy is basically a strategy to meet a limit state. So here's the limit state, here's the condition that we need to meet. And a design philosophy is basically saying, how are we going to meet that and account for the big word, which is uncertainties, okay? That's what a design philosophy is intended to do. And a factor of safety does handle that pretty easily. Just take the loads, double them, boom. There's your uncertainties. You don't have to worry about uncertainties because we just did that, okay? Or whatever you calculate for your strength, cut it in half, bam. Uncertainties are handled. That is a simple way, but it is not a very scientific way, okay? Now, just from a terminology perspective, that is termed allowable stress design, ASD, okay? That's what ASD is. It's just a factor of safety, okay? There is a more elegant way to do it, okay? Now, the reason for the more elegant way goes to reality, okay? Reality says that if I'm feeling very destructive, and instead of breaking one table, I break every table in this room, I'm going to get some scatter in that data. I can take that data, compute a mean, compute a standard deviation, I can predict, you know, like if I break 30 tables, I can predict with some degree of accuracy what's the strength of table number 31 or table number 32. That's the whole point of Stat 345, right? I mean, that's why you take that probability and statistics class, so that you can infer from data, right? Well, the problem with ASD is that it lumps all the uncertainties all into one bucket and just says, let's just use a factor of safety of 2. And we can actually categorize those in structural engineering pretty well. So for example, on the resistance side, we can quantify uncertainties with material quality. We can quantify uncertainties with construction practices and whatnot if we do the research and monitor that. Same thing with loads. I mean, for example, take snow loads. We've been collecting snow data for years, right? So we can tell you what the snow load is in Huntington, West Virginia, and give you some confidence interval as to whether or not that's right, okay? So we can actually handle that pretty accurately. So the problem with ASD is it lumps all the uncertainties together. What LRFD does, LRFD says, here's what we're going to do. We're going to treat the loads and the resistances separately, okay? And what we're going to do is we're going to apply essentially safety factors to the loads and safety factors to the resistances. So we call them load factors and resistance factors. And so we treat them separately. So we have different load factors for different factors for loads than we do for resistances. And what we find is we get a more accurate means of quantifying uncertainty. This is the whole nature of LRFD. Now I'm going to talk about this a little bit on Friday because I'm going to make this point a little bit more clearly. But if you open up your steel manual, so I do want to mention a couple things about ASD versus LRFD. In steel design, you still have the option of doing both. If you go to concrete design, you're only doing LRFD, okay? If you go to bridge design, you're only doing LRFD. To be honest, I don't think very many, I would say, the new generation of engineers are really using ASD. And my prediction is by the time that I'm of a retirement age, that ASD will probably be a thing of the past. But it is still present in the manual. And one of the ways that you can easily discern that is, I don't know if anybody has started opening their manual and just started flipping through it and seeing stuff like this. Has anybody seen this? If you open it, you will see these colored tables, okay? Anything that's green is ASD, and anything that's blue is LRFD, okay? So what we're going to be doing this semester is we're only going to be using LRFD. So if you open your manual and you need to do a problem, don't look up green numbers, look up blue numbers, okay? And you don't even need to take my opinion on whether or not LRFD is the better philosophy. You can actually open the FE reference manual and find that they're only reporting LRFD numbers. They're not reporting the ASD numbers. It's that, ubiquitous. Really, I think ASD is, I mean, I'm sure there's still some engineers that have been doing things for 30 years and don't really want to change, but I would think ASD is probably more useful now for folks at your age as a rating tool. And if you can do LRFD, ASD is actually, I would say, a little bit easier. So if you can do this, you can certainly do the other one. Okay. Now the way that LRFD works is that you basically quantify things on two sides of the equation. And so today, what we're going to focus on is the loads side. I've got some really fancy notation here with some Greek letters and all that, but the long and short of it is really what's in this box. Okay, this is if you understand what's in that box, you understand LRFD. Okay, and so to explain what's in this box, let's talk about resistances. Okay, so the way that it works is on the resistance side, resistance is all about strength. How much a connection or a member can hold up before it's going to fail. So like, for example, if we're talking about shear in bolts, so you have a bolt, how much load does it take to shear the bolt in half? So we calculate the load per bolt, or the capacity of each bolt in shear, how much it's going to take to snap that in half. Multiply that by the number of bolts that's in the connection, and boom, that's the capacity. Now, what this nominal capacity is, a nominal capacity is, the best way I can describe it is a prediction of what would happen if you took it to the hydraulic press channel and actually broke the element. Like Rn is what you would predict is the actual capacity. So it's based on mechanics, it's based on what's in the specifications, etc. That's what a nominal capacity is, or a nominal resistance. But what we all know is that there is uncertainty associated in that calculation. Just like there is uncertainty associated in the prediction of the capacity of the tables in this room. As we said last time, if I break this table and it breaks at 800 pounds, this one's probably not going to break at exactly 800 pounds. Maybe it's 806, maybe this one's 793, maybe this one's 801, you know, etc. There's probably going to be a hovering around a given average, but there's going to be some scatter. So we adjust that by an appropriate resistance factor. And so that resistance factor changes dependent upon the limit state that we're looking at. So a good example of what I mean by that is, so when we look at yielding limit states, a common resistance factor for yielding is 0.9, but a resistance factor for fracture is 0.75. So why is the resistance factor lower for fracture? Well, if a member yields, I mean, what happens from a mechanics perspective? Remember in materials, right? If you have a piece of metal and it yields, all that means is that it gets longer, right? That sucks, and that is bad if it's causing undue stresses in other elements, but it's certainly not as bad as fracture, right? I mean, imagine a piece of taffy, right? If the taffy yields, it just permanently elongates. If the taffy fractures, it cuts in half, right? So what's the more dangerous phenomenon, yielding or fracture? Fracture, right? So when we're looking at fracture limit states, we take our resistance and we chop it down more, right? Because it's a matter of safety, okay? So what we end up with is we take this nominal resistance and we adjust it and we get a factored resistance. So now we're dealing with a factored resistance, a PRN, a nominal resistance adjusted by a resistance factor. Now on the loads side, we do something similar. So on the load side, we have these various load components like snow, like wind, like earthquakes, like dead load, etc. We compute each of those loads separately. So we have a dead load, we have a live load, we have a snow load, etc. And then what we do is we combine those in what we call load combinations. And those load combinations are sort of responding to events that the structure would experience, and I'll talk about what those events are here in a little bit. But we then end up with a factored load, a series of loads that have been summed up, a series of loads adjusted by a load factor. So resistance factors are usually 1 or smaller than 1 because they're decreasing the load. For the most part, load factors are usually bigger than 1 because they're amplifying the loads. So we combine both of these effects, but at the end of the day, as long as the resistances are greater than or equal to the loads, structure's fine. This is a high-level view of what we're going to be doing the entire semester, okay? So if even now this is a little fuzzy, don't worry, we're going to get a lot of practice on this. It won't be that bad. All right. Sound good? Okay. Now, here are the LRFD load combinations that we use. I'm gonna go back to these and sort of explain these in detail here in a little bit, but the long and short is that these load combinations correspond to events that the structure is going to experience. Okay? So for example, these load combinations 6 and 7 are more intended for when the structure is experiencing an earthquake event. One of these is sort of an earthquake during normal operations, so there's some live load and some snow load. And this one's more intended for if it's a real earthquake, right? So without getting too far into the weeds on earthquake engineering, what I'll say is the E values and the way that you do this does get different, okay? Earthquake engineering is a thing in and of itself, so I won't get too far down the rabbit hole on it. For example, some of these loads, these load combinations 3 through 5 are more geared towards wind, right? And wind is also another one of those things that does get somewhat complicated. We're only going to cover it at a very high level. Not every load combination is going to be used for every member in a real world setting. So let me sort of explain what I mean by that. How many, all right, so let's, I'm going to use a different example. I'm going to tell you a story, but you'll kind of see what I mean. Okay, let's say that you are in a car with your friend. You are in the passenger seat. Your friend is driving. They are a horrible driver. They are going well above and beyond the speed limit. They see something in the road. They slam on their brakes. What's the first thing that you fling into? thank you very much for wearing your seatbelt. The very first time I asked that question, I got the dashboard, the windshield, the pavement. I was like, you all not wearing your seatbelts? Where are your seatbelts? Sorry. Okay. Side note. But let me explain what I mean by this, or how it relates. So when you're in a car and the car experiences an extreme event, it is not the entire car that resists you, right? That holds you back in the event of a collision. In a vehicle, we install a specific subsystem, right, called a seatbelt. And it is that seatbelt's only function to resist you in the event of a collision, right? So it's not the whole car that resists you, it's just a piece of that car. Does that make sense? The same thing is true in buildings, okay? So for example, here's a really easy one to kind of understand. All right, so let's say here's a building, and I'm going to draw the columns, and let's draw the beams. Okay, and let's say here's the ground. Okay, and let's say that the building experiences a lot of wind. Okay, now if the building is exposed to wind, okay, the building is going to want to topple over, right? We don't like buildings to topple over. So a simple way of arresting that is to maybe pick a bay and install some braces, right? Okay, so then what happens is this sort of part of the building, suddenly we go back to Dr. Mike's structural analysis class, and we got ourselves a little truss we have to solve, right? You know, we have a truss with a series of loads on it, and we just analyze the truss and size those members to resist those loads. Make sense, right? But here's the thing. So let's keep this context in our mind. Remember I've talked about this floor beam in this building, the floor beam right here? Does that floor beam is it really responsible for wind load, for resisting the building with respect to wind? No, right? So if I'm designing this beam, I don't have to worry about wind, you know? I only have to worry about wind for the wind force resisting systems, right? That makes sense? Okay. So this is what I'm saying here is that not every load combination is going to be used for every member. Now I bold 1 and 2 because those are the ones that pretty much are used for every member, okay? For the most part, okay? Load combination 2 is going to be the one that we use just about for every case every semester, okay? Load combination 2 is essentially normal operation of the structure. Every single structure in existence is subjected to dead loads and live loads. I really don't care what it is, and you'll understand why after today's lecture. Every structure is subjected to dead and live, and dependent upon where it is, maybe a little bit of environmental effects, like what's going on over here, and you'll understand what's going on over here in a bit. But when does this one happen? Okay, so let's have a thought experiment. So dead and live. Dead load is sort of related to the self-weight of the structure. Actually, you know what? I'm going to come back to this. Because I want to define these a little more rigorously. I'll come back to that here in a bit. I want to talk about what situations these two would represent. But I'll get to that here in a bit. Before I move on, does everybody kind of understand what I'm talking about? How not every load combo will be used for every member? Everybody good? Okay. Now, I say that with the caveat that on the homework assignment, I'm actually just going to give you some loads, and I want you to get the biggest ones. I'm going to kind of violate what I just said, but you'll see what I mean. Okay, let's talk about those structural load types. Now, I break, and all structural engineers break loads into two classes. We either have gravity loads or lateral loads. Gravity loads are ones that literally act in the direction of gravity, and lateral loads act left to right, like parallel to the earth, okay? Now, some of you might be thinking, wait a minute, that's 5 loads. Aren't there more? Just dead load, live load, snow load, wind, and earthquake? Like, some of you might be thinking, what about rain? Like, don't buildings have to withstand rain? Yeah, they do. But rain's a little different. First off, rain is usually something we can get rid of through proper drainage, right? We have roofs sloped like that. Rain comes off. And I'll say this, we usually don't like to have rain just stay on the roof. There are some instances during snow. So if you have a roof and you have snow on the roof and then the temperature rises and then it rains, the rain and the snow have a different density, so you add a rain on snow surcharge, but it's all sort of accounted for in the snow load. The only time that rain becomes a problem is if we have an effect called ponding. Ponding is something that we really want to avoid. We hate ponding. Let me explain what ponding is. So, let me go back. So ponding is what happens. Let's say you have, let's say some beam, and you put some water on top of it. So Dr. Waite would be happy if I put my little rain symbol, water symbol on there. Okay. Now let's say I have myself a little divot or some little deformation in the top of the beam. So I get myself like a little depression, like a little deep spot in the beam, right? Well, what happens is that deep spot allows for more water, right? So I can put more water in that, which is more force. More force makes that little deformation deeper, which creates room for more water, which makes more load, which makes it deeper. So it sort of like bends on it, it sort of builds on itself. That's called ponding, right? But that's more of a localized phenomenon than something we need to worry about globally. So actually, in terms of rain, we don't really count for rain all that often. But I do want to talk about the load types that we do account for very often. Now, I am going to mention a specification that we're not really going to use directly. Like, for example, the one we're going to use directly is this, okay? One of the things that you're just going to have to get used to as engineers are codes and specifications. There are just a lot of them, right? There's codes and specifications for steel, for concrete, for timber, for masonry, for bridges, for buildings, for loads, for example. I mean, like, that's just in structures land. Green book for transportation, you name it. There's just oodles and oodles of specifications. And one of the most common ones is ASCE 7. ASCE does a lot more than organized concrete canoes, okay? They are the technical representative of civil engineers in the United States. And so one of the things that ASCE is responsible for is the production and maintenance of technical specifications. One of the most popular ones, or most used ones, is ASCE 7. ASCE 7 outlines the minimum loads on buildings and structures. Let me explain why ASCE 7 is important, okay? Let's say that I'm designing a classroom, okay, a classroom. So I'm designing the floor system in a classroom. And so I think the people, I'm going to represent the people as a pounds per square foot. So the people, the desks, the chairs is a pound per square foot. What's a good number? What do you think I ought to use? 40? 50? Like, what should I use? I'm asking, okay? Okay, this is my point. That's your gut, right? What I'm saying is that ASCE 7 can establish a baseline that we all go by, okay? And that those loads come from actually instrumenting schools and hospitals and churches, etc., to actually see the loads that you should account for. What should the wind speed of a building in Huntington, West Virginia be? What's the number? You know what I mean? That's what ASCE 7 does, is it outlines those acceptable minimum load provisions so that we're all doing the same thing. That's what these specifications are intended to do. So it's incredibly important. I'm actually going to show you a hazard tool here in a bit. Okay, now I've mentioned dead loads and live loads. I do want to sort of rigorously define those. Now, I defined those in structural analysis slightly differently than I'm going to do here. When we were talking about influence lines last semester, I said that dead loads were permanent and live loads were transient. In other words, dead loads didn't move, live loads could. There's some analogies here. What I'm going to say, so I'm going to agree with the definition for permanency on dead loads. Dead loads primarily consist of the structure's own self-weight and any other load that is permanent. Dead loads don't move. The nice thing about dead loads is that they are easier to predict than live loads. And I want to follow up on that here in a bit. So for example, if we were talking about the floor system in this building, the floor systems, like the dead loads for this floor system, so up here, the beams up here have to be responsible for the drop ceiling. They have to be responsible for the mechanical, electrical, and plumbing allowance. They have to be responsible to hold up the fireproofing. They have to be responsible to hold up the deck pan, the concrete, the reinforcement, the carpet, like all those stuff. That's permanent. That's, you know, that's stationary. That's not going anywhere. And some of you might think, like, do you really have to account for carpet? Well, I don't know about you, but carpet is a lot lighter than tile, you know? Now, how heavy do you think tile is if it was over a room this big? It's not feathers, right? It's actually a little bit of load, right? So, so you do need to account for all of that. And then you get those details, you know, from the building plans and things like that. Most commonly, engineers will need to compute dead loads with either steel or reinforced concrete. The unit weight for structural steel is something you can set your watch by. So if you have a box of structural steel that's 1 foot by 1 foot by 1 foot and it's solid steel, it weighs 490 pounds. Concrete can vary, okay? Those of you who've had materials know that different batches of concrete can have different weights. An upper bound of normal weight concrete is about 145 pounds per cubic foot. We use 150 to account for the rebar that's inside it. We up it a little bit. So 150 is a pretty standard load for normal weight reinforced concrete. And unless otherwise stated, engineers are mostly using that. You can look up the loads for other components in a structure from a document like ASCE 7 or from the manufacturer. So for example, if you're using, let's say, this carpet, you know, in the building, the manufacturer of this carpet probably has a catalog that says what value you can use for a pound per square foot basis. If not, you can probably look that up in ASCE 7. ASCE 7 has oodles and oodles of tables, like here's a unit weight for masonry, here's a unit weight for tile and linoleum and all that stuff. So anything that's permanent, that's not going anywhere. So we have common dead loads, we have floor finishes, we have concrete, metal deck, fireproofing, the framing itself. You know, you just add it all up, okay? That's dead loads, okay? What about live loads? There is a word that you will hear me use with live loads pretty commonly. Sometimes I will use the term occupancy. Live loads are what the structure's being used for, okay? So, as you mentioned in classrooms that you suggested that a live load of 50 pounds per square foot, right? We actually see here specified 40, but you weren't that far off, right? Okay, so the live load in a classroom is typically taken to be 40 pounds per square foot, okay? Look here, we have corridors above the first floor. Why would we detail hallways to have a live load higher than 40 pounds per square foot? Why would we use 80 pounds per square foot for the hallways? Why? There's more traffic, right? That's one reason, right? Because you know, when class is let out, there's more people in the hallways, like on a per square foot basis, than there is in the classroom. And specifically, corridors on the first floor are probably gonna have a little bit more traffic. But what's another reason? Still, why would we want the load to be a little higher in the hallways? Fires. There you go. When there's an emergency, there's going to be a lot of people in the hallways, right? When there's an emergency, there's going to be a lot of people, so we need to make sure the building can account for that. Good answer. Okay? Now, again, occupancy, what the building is used for. Why is the live load in classrooms 40 pounds per square foot versus in libraries when it's 150 pounds per square foot? Why would the live load in a library be 150 pounds per square foot? The books, right? Because the library is full of a bunch of books that college students don't read, right? So, that was a joke, not very funny. or maybe it was kind of funny, I don't know. But in all seriousness, because the library is serving a different function, the library's loads are heavier, right? That should make sense. One of the things that this actually begins a very interesting discussion about how to design different types of buildings. For example, there is a very serious difference in how a structural engineer would go about designing a hotel versus designing a spec office building. So if you're designing a hotel, right? If you've ever been in a hotel, there's a very clear delineation as to where the hallways are and where the rooms are, right? And that doesn't really rearrange very often, right? I mean, the rooms are where the rooms are, the halls are where the halls are, okay? But in a spec office building, that might not be the case. If you've ever been in I mean, how many of you have ever been just like in a large office building with cubicles and things like that? I'm sure many of you have, okay? So what happens is if you're a developer and you are wanting to build a commercial office building, what you want is some flexibility on how to lease that space out. So like what happens is you have this office building and an accountant firm comes in and you're the owner of the building, so you charge rent on a per square foot basis, right? So the accountant comes in and says, I need 2,500 square feet, and say, okay, here's your space, here's how much it costs. But what you don't want is to be hampered by, well, these can only be hallways and these can only be offices. You want to be able to cordon that space out however makes sense, you know? So if you're an engineer designing a commercial spec office building, it's not that uncommon to size the whole floor as if it was one big hallway, because you don't know how it's going to be arranged, right? So I just throw that out there as some differences in how the designs work. Okay. Now, I told you that, if I go back a couple slides, I told you that these two combinations are the most common because all structures are subjected to their own self-weight, and all structures are subjected to whatever their intended occupancy is, right? You're not going to go through the exercise of building a library without putting some books in it, right? All structures are going to have their own self-weight and whatever they're being used for, okay? So you've got these numbers. So if we only consider dead load and live load, if that's all we consider, okay? So we have this load combination. Let's take a look at this load combination. 1.2 dead plus 1.6 live. So let's say that a beam, let's say this beam only has two loads on it, dead and live. Why do you think that the load factor for the live, why is it 1.6 and the dead load is 1.2? Why is the load factor for live loads higher than that for dead loads? Why?
Because the live loads are less predictable.
That's exactly right. It's 100% right. We are more uncertain with dead loads than we are live loads. I can probably predict the dead loads on an element with much more accuracy than I can predict how heavy the sum total of students are in a classroom on a beam, right? So we up the live load factor a little bit to account for that uncertainty. That's where LRFD comes in. It handles those uncertainties differently, okay? Does that make sense? Now, let me ask you a further question, okay? So if that's the case, why would we even have that load combo to begin with? I mean, why would we ever consider just dead load? I mean, if you're building structures to support people and support occupancy and support loads, why would we ever have that? Why would we ever have a load combo that's 1.4 dead? When is a structure ever going to see just dead load? During construction. That's 100% right. Because during construction, there are no books in the library because there's no library yet, right? So structures have to survive construction as well, right? So during construction, we have to have a load combo that just handles for that. And why is it 1.4? Well, wait a minute. It's 1.2 here. Why is it 1.4? Well, it's 1.4 to achieve a target uniform level of safety. That's what it's for. That's what these effects are for. Does that make sense? Okay, I just throw that stuff out there to make sure everybody's clear. Okay, snow loads. Snow loads. Snow loads are obviously a function of where you're at in the United States. For example, this is the snow load map for the United States. This is from an older edition of the spec, admittedly, but the patterns aren't really all that different. There is one state that has its own snow map by itself. Which state is that? Well, okay, so Colorado has some specific notes, but he's right too. Alaska's going to have its own snow map because it's Alaska, right? The snow load. So just so everybody's aware, what happens with snow loads is oh, sorry, I didn't do that. Do this. So what happens with snow loads is what ASCE7 reports, and we're not going to get into the weeds on this. I could teach a whole college course just on how to do loads on structures. It would be a very fun class to teach, but I'm not going to get into the details here. I'm just going to get into the high level. So the way ASCE7 works is ASCE7 reports what are called ground snow loads. So these are the upper level, upper bound snows that you could expect on the ground. And then it is your responsibility to convert those to loads that you would see on the roof. Okay, and there's a lot that goes into that. For example, is the roof flat or is it on an incline? We have to do some trigonometry for that. Is the building heated? Like, it might sound silly, but the snow loads on a greenhouse are going to be different than the snow loads on a building like this because the roof has some heat to it, and heat melts snow. I think that, I learned that in middle school science or something like that. That was a joke, not a very funny one. But another thing to consider with snow is what's called snow drift. So has anybody ever been on top of a office building or commercial building kind of like this? Anybody ever been on a roof like that? Like, what does the roof look like? Is it like this? It's flat, right? And there's usually like gravel or something like that on the roof. And there's usually like a little wall like that. And here's the gravel. And here's you with very weird proportions. There's you. Okay, so you get a little bit of snow on the ground, right? And then the wind blows, and you get a bunch of snow that piles up here on this barrier. And it's almost like you get this triangular load that you put on a beam that Dr. Mike said, yeah, you deal with triangular loads. And you're like, no, you don't. I'm like, there you go. Here you do. So this is an idea for when, so the different things that you have to consider with snow loads. Wind loads. Wind loads are also a function of where you're at in the United States. Now, why is it that the wind speed is pretty much the same everywhere in the country except for the coasts? Why is the wind speed different on the coasts? What happens on the coasts that makes the wind speeds higher? Hurricanes. Basically the same thing. Yeah, hurricanes, right? So here out in Florida, we got some pretty high wind loads because of the potential for hurricanes, right? So out here in Huntington, West Virginia, we don't have to worry about that. But out in the main body of out in the coastal regions, we have to up those wind speeds a little bit. Plus, just even if hurricanes aren't an issue, just the nature of wind in coastal regions. I mean, how many of you have ever been to the beach and noticed it's just windy? I mean, that's kind of a feature of the beach is that it's just a windier area. Typically what you do with wind loads is it's sort of similar, like you're getting the wind speed in the geographical region where you're at, and then you need to convert that to the wind pressures that the building experiences for the purposes of design. I'll sort of give you an example. How many of you, is there anybody here that's ever been on top of the Empire State Building? Anybody ever been there? Okay, have you ever been on the observation decks, like on the 88th floor, like outside? Was it windy? Yeah, it was windy, right? Wind speeds and wind pressures on buildings vary as a function of height, okay? So if you're designing for gravity loads, just gravity up and down, a floor beam on the 3rd floor behaves the same way as the floor beams on the 83rd floor because it's just gravity. But wind is different. Wind, if you want to know what makes tall building design complicated, it's not gravity, it's lateral effects. It's wind and earthquakes. The wind resisting system in this building is easier to detail and fabricate than the wind resisting system in Smith Hall. Because Smith is tall, right? The taller a building gets, the harder wind gets, okay? And there's sort of a parabolic distribution of wind force. As you get taller, the winds get crazier. Last thing I want to mention are earthquakes. Earthquakes are not something that we need to worry about here in this region of the country, but it's not to say you don't worry about it at all. The thing about earthquakes is earthquakes do not, you don't apply a force to a building in an earthquake. There's no earthquake monster pushing on a building, okay? Instead, with earthquakes, you have accelerations. So what's happening with earthquakes is the ground causes the building to accelerate. The example I mentioned earlier about being in the car and suddenly hitting the brakes, the reason that you fling into the seatbelt is not because there's a car crash monster that pushed you into the seatbelt. What happened was you were going a certain speed, and then that speed suddenly changed. So you underwent a sudden change in acceleration, and as a result, you moved. The resisting system, the seatbelt, is what applies force to you. Okay, so what happens? So sort of like the way it works is you have the building undergoes like a lateral acceleration, and what we can do is, so essentially, like we sort of treat like each floor as a big old lump of mass, and we distribute the force to each floor, and suddenly, we have these earthquake forces that we can plug into MassTan or some other structural analysis package and analyze the structure. But they're not like forces that are physically applied to the structure. They're just calculations essentially from F equals ma. Okay. Now, just to give you kind of an idea, this is about what the seismic dangers are, the seismic hazard levels in the United States. So where we're at in the United States, we're not that bad. We're really not. But you would be surprised. I mean, we have a fault line right here. So if you're designing structures out in, Western Kentucky, you've got some seismic loads to consider, probably more than you thought you would. Now, I mean, obviously, here out in California or here along the Ring of Fire in Alaska. Alaska is a really weird place to design structures because we've got really high snow loads, we've got really high wind loads because most people live on the coast, and it's along the Ring of Fire, so we have earthquake loads. So it's a really weird place to design structures. So I just wanted to mention that. I'm going to discard my annotations. Okay, anybody have any questions? So I just want to show you the homework real quick, just to, again, like I said, it's really easy, okay? So basically what I've done is I've given you 4 values: a dead load, a live load, a snow load, and a wind load, and I just want you to go through the load combos and find the biggest one. That's it. That's the homework, okay? So the way it's going to work is there's a field in Blackboard. You just type it in, and that's it. You can submit multiple times, and it will grade the highest one. So again, this is not really meant to be some super challenging assignment from a grade perspective. The other thing I'll mention is that if you ever see like an OR, so like 1.2 dead plus 1.6 live plus 0.5 times OR, just take the maximum of these 3. And so in the case of this one, LR or S or R, there is no LR or R, so just 0.5X, So you just go through these, take the maximum one, that's your answer. You do not need to evaluate every one of them. Like if you take a look at these equations and take a look at the values, some of them you can skip, okay? And I'm not asking you to upload a PDF for this. I'm just asking you to input the number, So again, this is just to get you familiar with it. Again, I told you, real quick homework assignment. You could probably have it done before 10 a.m. So, although it opens at 10 a.m. So, any questions? All right, I'm gonna pull up the QR code one more time, but that's all I have, everybody. I will see you all on Friday.